Module 2.3 Reversible Reactions. At equilibrium, the rate of reaction is identically to zero for all the species, that is, minus Ra equal to zero. Then, for the general reaction, A of A plus B of B gives us C of C plus D of D, and the reverse reaction C of C plus D of D gives us A of A plus B of B, we have that the concentration at equilibrium are related by the equilibrium constant capital K C. So capital KC is equal to the concentration of C at equilibrium elevated to the stoichiometric coefficient C times the concentration of D at equilibrium elevated to the stoichiometric coefficient D divided by the concentration of A at equilibrium elevated to the stoichiometric coefficient A times the concentration of B at equilibrium elevated to the stoichiometric coefficient B. The units of the thermodynamic equilibrium constant Kc are moles divided by liters elevated to the difference of coefficients D plus C minus B minus A. Let us combine the two molecules of benzene to form a molecule of hydrogen and one of diphenyl. In this discussion, we shall consider this gas phase reaction to be elementary and reversible. So, here we have 2 of benzene will give us 1 of diphenyl plus 1 of hydrogen. We will call the rate constant to the right Kb, and we will call the rate constant to the left K minus B. So symbolically, we can put this reaction as 2 of B will give us D plus H2, or in the reverse, D plus H2 will give us 2 of D. Benzene, in which case is B, is being depleted by the forward reaction. 2 of benzene at a rate constant Kb will give us 1 of diphenyl plus 1 of hydrogen. Here, the rate of disappearance of benzene is minus Rb forward is equal to Kb times the concentration of B elevated to the second power. If we multiply both sides of this equation by minus 1, we obtain the expression for the rate of benzene for the forward reaction. So here we have Rb forward is equal to minus Kb times the concentration of B elevated to the second power. And for the reverse reaction between diphenyl D and hydrogen H2, we will have that 1 molecule of diphenyl plus 1 molecule of hydrogen will give us 2 molecules of benzene, and the rate constant will be K minus B. So the rate of formation of benzene is given as Rb reverse equal to K minus B times the concentration of D times the concentration of H2. The rate constant Kb and K minus B are defined with respect to benzene. And the rate of formation of benzene, which is the net rate, will be equal to the rate of Rb forward plus Rb reverse. And this was going to be Rb is equal to minus Kb times the concentration of B to the second power plus K minus B times the concentration of D times the concentration of H2. If we multiply both sides by minus 1, we obtain the rate law for the rate of disappearance of benzene, which is minus Rb. So minus Rb is equal to Kb times the concentration of B to the second power minus K minus B times the concentration of D times the concentration of H2. And this is equal to Kb that will multiply to the concentration of B to the second power minus K minus B divided by Kb times the concentration of D times the concentration of hydrogen. And if we replace the ratio of the reverse and forward rate load constants by the equilibrium constant, we will have that minus Rb is going to be Kb times the concentration of B to the second power minus the concentration of D, the concentration of hydrogen divided by the equilibrium constant Kc. And here, Kb divided by K minus B is equal to the equilibrium constant Kc. Now, let's write the rate of formation of diphenyl Rd in terms of the concentration of hydrogen, diphenyl, and benzene. The rate of formation of diphenyl is Rd equal to Kd times the concentration of B to the second power minus the concentration of D, the concentration of A2 divided by the equilibrium constant Kc, and using the relations given for the general reaction that the rate of A, Ra, divided by the stoichiometric coefficient of A is equal to the rate of B divided by the stoichiometric coefficient of B is equal to the rate of C divided by the stoichiometric coefficient of C, and is equal to the rate of D divided by the stoichiometric coefficient of D. And here we know that if A and B are disappearing, we need to consider the minus sign in these expressions. We can obtain the relationship between the various species reaction rates Kb and Kd. So the rate of D divided by 1, which is the stoichiometric coefficient of D, is equal to the rate of B divided by minus 2, which is equal to stoichiometric coefficient of B. So this will be equal to Kb divided by 2 multiplied by the concentration of B to the second power minus the concentration of C times the concentration of D divided by the equilibrium constant Kc. And if we compare these equations, we see that the relationship between the specific reaction rate with respect to benzene is that the rate constant Kd is equal to the rate constant Kb divided by 2.